In this video, we'll apply the divide and conquer algorithm design paradigm to the problem of multiplying matrices. This will culminate in the study of Strassens matrix multiplication algorithm. And this is a super cool algorithm for two reasons. First of all, Strassens algorithm is completely non-trivial. It's totally non-obvious, very clever, not at all clear how Strassen ever came up with it. The second cool feature is it's for such a fundamental problem. So computers, as long as they've been in use, from the time they were invented up till today, a lot of their cycles is spent multiplying matrices because it just comes up all the time in important applications. So let me first just make sure we're all clear on what the problem is of multiplying two matrices. So we're going to be interested in three matrices, x, y, and z. I'm going to assume they all have the same dimensions, n by n. The ideas we'll talk about are also relevant for multiplying non-square matrices, but we're not going to discuss it in this video. The entries in these matrices, you could think of it as whatever you want. Maybe they're integers, maybe they're rationals, maybe they're from some finite field. It depends on the application, but the point is they're just entries that we can add and multiply. So how is it that you take two n by n matrices, x and y, and multiply them, producing a new n by n matrix, z? Well, recall that the ij entry of z, that means the entry in the ith row and the jth column, is simply the dot product of the ith row of x with the jth column of y. So if ij was this red square, this red entry over in the z matrix, that would be derived from the corresponding row of the x matrix and the corresponding column of the y matrix. And recall what I mean by dot product. That just means you take the products of the individual components and then add up the results. So ultimately, the zij entry boils down to a sum over n things, where each of the constituent products is just the xik entry, the ik entry of the matrix x with the kj entry of the matrix y, or here k is ranging from 1 to n. So that's how zij is defined for a given pair of indices I and j. One thing to note is that where we often use n to denote the input size, here we're using n to denote the dimension of each of these matrices. The input size is not n. The input size is quite a bit bigger than n. Specifically, each of these are n by n matrices and contains n squared entries. So since presumably we have to read the input, which has size n squared, and we have to produce the output, which also has size n squared, the best we could really hope for a matrix multiplication algorithm would be a running time of n squared. So the question is, how close can we get to it? Before we talk about algorithms for matrix multiplication, let me just make sure we're all crystal clear on exactly what the problem is. So let's just actually spell out what would be the result of multiplying two different 2 by 2 matrices. So we can parameterize two generic 2 by 2 matrices by just giving the first one entries A, B, C, and D, where these four entries could all be anything. And then we're multiplying by a second 2 by 2 matrix. Let's call its entries E, F, G, and H. Now, what's the result of multiplying these? Where again, it's going to be a 2 by 2 matrix where each entry is just the corresponding dot product of the relevant row of the first matrix and column of the second matrix. So to get the upper left entry, we take the dot product of the upper row of the first matrix and the first column of the left column of the second matrix. So that results in AE plus BG. To get the upper right entry, we take the dot product of the top row of the left matrix with the right column of the second matrix. So that gives us AF plus BH. And then filling in the other entries in the same way, we get CE plus DG and CF plus DH. Here. So that's multiplying two matrices, and we've already discussed the definition in general. Now, suppose you had to write a program to actually compute the result of multiplying two n by n matrices. One natural way to do that would just be to return to the definition, and which defines each of the n squared entries in the Z matrix as a suitable sum of products of entries of the X and Y matrices. So in the next quiz, I'd like you to figure out exactly what would be the running time of that algorithm as a function of the matrix dimension n, where as usual we count the addition or multiplication of two individual entries as a constant time operation. So the correct response to this quiz is the third answer. that the running time of the straightforward iterative algorithm runs in cubic time relative to the matrix dimension n. To see this, just recall what the definition of the matrix multiplication was. The definition tells us that each entry zij of the output matrix Z is defined as the sum from k equal 1 to n of xik times ykj. That is the dot product of the ith row of the X matrix and the jth column of the Y matrix. I'm certainly assuming that we have the matrices represented in a way that we can access a given entry in constant time. And under that assumption, remember each of these products only takes constant time. And so then to compute zij, we just have to add up these n products. So that's going to be theta of n time to compute a given zij, and then there's an n squared entries that we have to compute. There's n choices for I, n choices for j, so that gives us n squared times n, or cubic running time overall for the natural algorithm, which is really just a triple for loop which computes each entry of the output array separately using the dot product. So the question, as always, for the keen algorithm designer is, can we do better? Can we beat n cubed time for multiplying two matrices? And we might be especially emboldened with the progress that we've already seen in terms of multiplying two integers. We apply the divide and conquer algorithm to the problem of multiplying two n-digit integers, and we had both a naive recursive algorithm and a seemingly better algorithm due to Gauss, which made only 3 recursive calls. Now, we haven't yet analyzed the running time of that algorithm, but as we'll see later, that does indeed beat the quadratic running time of the grade school algorithm. So it's very natural to ask, can we do exactly the same thing here? There's the obvious n-cubed algorithm, which follows straight from the definition. Perhaps analogous to Gauss, we can have some clever divide and conquer method which beats cubic time. So that's what we're going to explore next. Let's recall the divide and conquer paradigm. What does it mean to use it? Well, we first have to identify smaller subproblems. So if we want to multiply two n by n matrices, we have to identify multiplications of smaller matrices that we can solve recursively. Once we've figured out how we want to divide the given problem into smaller ones, then in the conquer step, we simply invoke our own algorithm recursively. That's going to recursively multiply the smaller matrices together. And then, in general, we'll have to combine the results of the recursive calls to get the solution for the original problem, in our case, to get the product of the original two matrices from the product of whatever submatrices we identify. So how would we apply the divide and conquer paradigm to matrices? So we're given two n by n matrices, and we have to somehow identify smaller pairs of square matrices that we can multiply recursively. So the idea, I think, is fairly natural. So we start with a big n by n matrix X. Right, so there's n rows and n columns, and we have to somehow divide it into smaller pieces. Now, the first thing you might think about is you put it into its left half and its right half, analogous to what we've been doing with arrays. But then we're going to break X into two matrices which are no longer square, which are n over 2 in one dimension and have length n in the other dimension. And we want to recursively call a subroutine that multiplies square matrices. So what seems like the clear thing to do is to divide X into quadrants. Okay, so we have 4 pieces of X. Each is going to be n over 2 by n over 2, corresponding to the different quarters of this matrix. So let's call these different quadrants, or blocks, in matrix terminology, A, B, C, and D. All of these are n over 2 by n over 2 matrices. As usual, for simplicity, I'm assuming that n is even, and as usual, it doesn't really matter. And we can do the same trick with Y. So we'll divide Y into quadrants, n over 2 by n over 2 matrices, which we'll call E, F, G, and H. So one thing that's cool about matrices is when you split them into blocks and you multiply them, the blocks just behave as if they were atomic elements. So what I mean by that is that the product of X and Y can be expressed in terms of its quadrants. And each of its 4 quadrants, each of its 4 corners, can be written as a suitable arithmetic expression of the quadrants of X and Y. So here's exactly what those formulas are. They're exactly analogous to when we just multiplied a pair of 2 by 2 matrices. So I'm not going to formally prove this fact. I'm sure many of you have seen it before, or familiar with it. And if you haven't, it's actually quite easy to prove. It's not obvious. You can't see it off the top of your head necessarily. But if you go back to the definition, it's quite easy to verify that indeed, when you multiply X and Y, you can express its quadrants, its blocks, in terms of the blocks of X and Y. So So what we just did is completely analogous to when talking about integer multiplication and we wanted to multiply two integers, little x and little y, and we broke them into pairs of n over 2 digits. And then we just took the expansion and we observed how that expansion could be written in terms of products of n over 2 digit numbers. Same thing going on here except with matrices. So now we're in business as far as a recursive approach. We want to multiply x and y, they're n by n matrices, but we recognize we can express that product x times y in terms of the products of n over 2 by n over 2 matrices, things we're able to multiply recursively, plus additions. And additions is clearly easy. To multiply two different matrices with, say, n squared entries each, is going to be linear in the number of entries. So it's going to be n squared time to add two matrices that are n by n. So this immediately leads us to our first recursive algorithm. To describe it, let me quickly rewrite that expression we just saw on the previous slide. And now our first recursive algorithm is simply to evaluate all of these expressions in the obvious way. So specifically in step 1, we recursively compute all of the necessary products and observe that there are 8 products that we have to compute, 8 products of n over 2 by n over 2 matrices. There are 4 entries in this expansion of x times y. Each of the blocks is the sum of 2 products, and none of the products reoccur. They're all distinct. So naively, if we want to evaluate this, we have to do 8 different products of n over 2 by n over 2 matrices. Once those recursive calls complete, then all we do is do the necessary 4 additions. As we discussed, that takes time proportional to the number of entries in the matrix, so this is going to take a quadratic time overall, quadratic in n, linear in the number of entries. Now, the question you should be asking is this a good algorithm? Was this good for anything, this recursive approach, splitting x and y into these blocks, expanding the product in terms of these blocks, then recursively computing each of the blocks? And I want to say it's totally not obvious. It is not clear what the running time of this recursive algorithm is. I'm going to go ahead and give you a spoiler, which is going to follow from the master method that we'll talk about in the next lecture. But it turns out with this kind of recursive algorithm, where you do 8 recursive calls, each on a problem with dimension half as much as what you started with, and then do quadratic time outside, the running time is going to be cubic. So exactly the same as with the straightforward iterative algorithm that follows from the definition. That was cubic, it turns out, and that was clearly cubic. This one, although it's not obvious, is cubic as well. So no better, no worse than the straightforward iterative algorithm. So in case you're feeling disappointed that we went through all this work and this sort of seemingly clever divide and conquer approach for matrix multiplication and came out at the end no better than the iterative algorithm, well, there's really no reason to despair. Because remember, back in integer multiplication, we had a straightforward recursive algorithm where we had to do 4 recursive calls, products of n over 2-digit numbers. But then we had Gauss's trick, which said, oh, if we only did more clever products and more clever additions and subtractions, then we can get away with only 3 recursive calls. And we'll see later that that is indeed a significant savings in the time needed for integer multiplication. And we've done nothing analogously clever to Gauss's trick for this matrix multiplication problem. All we did is the naive expansion in terms of submatrices and the naive evaluation of the resulting expressions. So the $64,000 question is then, can we do something clever to reduce the number of recursive calls from 8 down to something lower? And that is where Strassens' algorithm comes in. So at a high level, Strassens' algorithm has 2 steps, just like the first recursive algorithm that we discussed. It recursively computes some products of smaller matrices, n over 2, or roughly n over 2 by n over 2 matrices. But there's only going to be 7 of them. They will be much less straightforward. They will be much more cleverly chosen than in the first recursive algorithm. And step 2 then is to actually produce the product of x and y, produce each of those 4 blocks that we saw with suitable additions and subtractions of these 7 products. And again, these are much less straightforward than in the first recursive algorithm. And so while the additions and subtractions involved will be a little bit more numerous than they were in the naive recursive algorithm, it's only going to change the work in that part of the algorithm by a constant factor. So we'll still spend only theta of n squared work adding and subtracting things, and we get a huge win in decreasing the number of recursive calls from 8 to 7. Now, just in case you have the intuition that shaving off 1 of 8 recursive calls should only decrease the running time of an algorithm by 1/8, by 12.5%, in fact, it has a tremendously more amplified effect because we do 1 less recursive recursive call over and over and over again as we keep recursing in the algorithm. So it makes a fundamental difference in the eventual running time of the algorithm, as we'll explore in detail in the next set of lectures when we discuss the master method. So again, a bit of a spoiler alert. What you're going to see in the next set of lectures is that indeed Strassens' algorithm does beat cubic time. It's better than n cubed time. You'll have to watch the next set of lectures if you want to know just what the running time is, but I'm going to tell you now that savings of the 8th recursive call is what changes the algorithm from cubic to subcubic. Now, 1969 was obviously quite a bit before my time, but by all accounts, from people I've talked to who were around then and from what the books say, Strassens' algorithm totally blew people's minds at the time. Everybody was assuming that there's no way you could do better than the iterative algorithm, the cubic algorithm. It just seemed that matrix multiplication intuitively fundamentally required all of the calculations that are spelled out in the definition. So Strassens' algorithm is an early glimpse of the magic and of the power of clever algorithm design. That if you really have a serious ingenuity, even for super fundamental problems, you can come up with fundamental savings over the more straightforward solutions. So those are the main points I wanted to talk about Strassens' algorithm, how you can beat cubic time by saving a recursive call with suitably chosen clever products and clever additions and subtractions. Maybe a few of you are wondering, what are these cleverly chosen products? Can you really do this? And I don't blame you. There's no reason to believe me just because I sort of spelled out this high-level idea. It's not obvious this should work. You might want to actually see the products. So for those of you like that, this last slide is for you. So here is Strassens' algorithm in its somewhat gory detail. So let me tell you what the 7 products are that we're going to form. I'm going to label them P1 through P7, and they're all going to be defined in terms of the blocks of the input matrices X and Y. So let me just remind you that we think of X in terms of its blocks, A, B, C, D, and we think of Y in terms of its blocks, E, F, G, H. And remember, A through H are all n over 2 by n over 2 submatrices. So here are the 7 products, P1 through P7. P1 is A times quantity F minus H. P2 is quantity A plus B times H. P3 is C plus D times E. P4 is D times G minus E. P5 is quantity A plus D times quantity E plus H. P6 is quantity B minus D times quantity G plus H. And finally, P7 is quantity A minus C, E plus F. So I hope you'll agree that these are indeed only 7 products, and we could compute these with 7 recursive calls. So we pre-process with a little bit of additions and subtractions. We have to compute F minus H, A plus B, C plus D, and so on. We compute all of these new matrices from the blocks, and we can then recursively, with 7 recursive calls, do these 7 products that operate on n over 2 by n over 2 matrices. Now, the question is, why is this useful? Why on earth would we want to know the values of these 7 products? So the amazing other part of the algorithm is that from just these 7 products, we can, using only addition and subtraction, recover all 4 of the blocks of a x times y. So x times y, you'll recall we expanded in terms of the blocks. So we previously computed this to be AE plus BG in the upper left corner, and then similarly expressions for the upper right, lower left, and lower right blocks. So this we already know. So the content of the claim is that these 4 blocks also arise from the 7 products in the following way. So the claim here is that these 2 different expressions for x times y are exactly the same, and they're the same block by block. So in other words, what the claim is that this crazy expression, P5 plus P4 minus P2 plus P6, where those are 4 of the products that we've listed above, that is precisely AE plus BG. Similarly, we're claiming that P1 plus P2 is exactly AF plus BH. That's actually easy to see. P3 plus P4 is CE plus DG. That's also easy to see. And then the other complicated one is that P1 plus P5 minus P3 minus P7 is exactly the same as CF plus DH. So all 4 of those hold. So let me, just so you believe me, because I don't know why you would believe me unless I actually showed you some of this derivation. Let's just look at the proof of one of the cases of the upper left corner. So that is, let's just expand out this crazy expression, P5 plus P4 minus P2 plus P6. What do we get? Well, from P5, we get AE plus AH plus DE plus DH. Then we add P4, so that's going to give us plus DG minus DE. Then we subtract P2, so that gives us a minus AH minus BH. And then we add in P6. So that gives us a BG plus BH minus DG minus DH. Okay, so what happens next? Well, now we look for cancellations. So we cancel the AHs, we cancel the DEs, we cancel the DHs, we cancel the DGs, we cancel the BHs, and holy cow, what do we get? We get AE plus BG. That is, we get exactly what we were supposed to in the upper left block of x times y. So we just actually verified that this equation holds for the upper left block. It's quite easy to see that it holds for the upper right and lower left blocks, and then a comparable calculation verifies it for the lower right blocks of the two. So summarizing, because this claim holds, because actually we can recover the 4 blocks of x times y from these 7 products, Strassens' algorithm works in the following way. You compute the 7 products P1 through P7 using 7 recursive calls. Then you just compute the 4 blocks using some extra additions and subtractions as shown in the claim. So 7 recursive calls on n over 2 by n over 2 matrices plus n squared work to do the necessary additions. And as you'll see in the master method lecture, that is actually sufficient for subcubic time. Now, I sympathize with you if you have the following question, which is, how on earth did Strassen come up with this? And indeed, this sort of illustrates the difference between checking somebody's proof and coming up with a proof. Given that I told you the magical 7 products and how you, from them, can recover the 4 desired blocks of x times y, it's really just mechanical to see that it works. It's a totally different story of how do you come up with P1 through P7 in the first place. So how did Strassen come up with them? Honestly, your guess is as good as mine.